Dear students, we will continue partial derivatives. This is question number 53 to 58. The question is, find all the second partial derivatives of the given functions. In question number 53, we are given a function which is the function of two variables x and y, and that is x4 y minus 2x cube y square. We need to find all the second partial derivatives of this function. So in order to find the second derivative, first of all we need to find the first derivative with respect to x and first derivative with respect to y. Now for second partial derivatives, we need to find the second derivative of this function with respect to x and the second derivative of this function with respect to y, then the second derivative of this function with respect to x then y, and then second derivative of this function with respect to y then x. So we need all those partial derivatives: fx, second derivative with respect to x, first derivative with respect to y, second derivative with respect to y, and second derivative with respect to x then with respect to y, and lastly second derivative of f with respect to y then with respect to x. Usually the answer of these two are always same whenever the function is continuous and differentiable. Anyways, let us start. First of all, we need to find the partial derivative of f with respect to x. So that is fx equal to partial derivative of this function with respect to x. So that is the difference rule, multiplying the derivative inside with both the terms, and that is the derivative with respect to x. So y will be kept constant. So y will be kept constant, and here y square will be kept constant and 2 as well. So that's why we have extract this y out of this derivative, and similarly 2y square is out from this derivative. 2 is missing here, we need to write 2 here. Now 2 is here. That is simple power rule. A partial derivative of x power 4 is 4x cube, and that is 3x square. Multiplying these terms and these two as well, we will get 4x cube y, and that is 2 3s are 6, x square then y square. So that is the first derivative of this f with respect to x. Now for second derivative with respect to x, we need to partially differentiate this first derivative with respect to x. So partial derivative with respect to x of fx, that is fx, replace fx by its own value, and then that is the difference rule. We need to multiply this derivative inside, and because that is the derivative with respect to x, so 4y will be kept constant, and here 36, here is a mistake. So that is the partial derivative of this function with respect to x. That is the partial derivative with respect to x, so 4y will be kept constant, and we have got the derivative of x cube, and similarly 6y square will be kept constant, and we are left with partial derivative of x square. The partial derivative of x cube is simply a power rule, and that is again power rule. Multiplying these terms, 3 4s are 12, x square y minus 6 2s are 12, x y square. So that is the second derivative with respect to x. Similarly, we need to find the second derivative with respect to x then with respect to y, because we have got the first derivative with respect to x, so taking the second derivative with respect to y. So that is actually partial derivative of fx with respect to y. So that is del y of fx, that is the value of fx, replacing the value, and then multiplying del y inside. So that is the partial derivative with respect to y. So 4x cube will be kept constant, and we are left with the partial derivative of y. Minus 6x square will be kept constant, and we are left with the partial derivative of y square. Now that is actually 1, and that is by power rule, that is 2y. So 4x cube, 6 2s are 12, x square y is the second derivative of f with respect to x, then with respect to y. Now coming towards the partial derivative with respect to y of the given function. So the first partial derivative of this function with respect to y is actually del y of this f, and this f is actually this function. Now multiplying this inside, keeping x constant, so we are left with del y of this y, and keeping 2x cube constant, and we are left with partial derivative of y square. This is equal to 1, and this is by power rule 2y. Now that is x4 into 1 is x4, minus 2 2s are 4, x cube y is the first partial derivative of y of f with respect to y. Now second derivative of f with respect to y again, that is the partial derivative of fy with respect to y. So partial derivative of fy with respect to y is, this is actually fy, so replacing fy by its own value, and partial derivative of this function with respect to y is actually this thing. This is actually constant, 4x cube is constant, so we are left with partial derivative of y. Now x is considered to be constant regarding the partial derivative of with respect to y, so the partial derivative of this function, of this term, will be equal to 0, and that is 4x cube into 1, and that is equal to minus 4x cube. So that is the second partial derivative with respect to y. Now secondly, partial derivative of fy with respect to x. So partial derivative of fy with respect to x, this is fy from here, this thing, so replacing fy and multiplying this derivative inside, so that is del x of x4, 4y is kept constant, so that is del x of x cube. That is actually a power rule 4x cube, and this is again power rule 3x square. So 4x cube minus 4 3s are 12, x square into y is the second partial derivative of f with respect to y, then with respect to x. So we see that the value of these two, just look at the answer, 4x cube minus 12 x square y, 4x cube minus 12 x square y, those two will always be the same if the function is continuous and differentiable. So that is how we need to find the second partial derivative of the given function. These questions are 53 from 258, and this slide another question is solved, that is question number 56. That is the same question, but we are given a function in this fashion that t is equal to e power minus 2r cos of theta. So we see that t is the function of r and theta, so t is the function of r and theta. So we need to find the partial derivative, second partial derivative of this t with respect to r, then with respect to theta, then second derivative with respect to r, second derivative with respect to theta, second derivative with respect to r then theta, and then second derivative with respect to theta then r. So we need all those derivatives, partial derivatives, tr, t double r, tr theta, t theta, and t double theta, then t theta r. So that is the same process. Tr means partial derivative of this function with respect to r. Now with respect to r, theta will be kept constant, so cos of theta is written outside this derivative, and that is the derivative of e power u. What is the derivative of e power u? That is the same e power u into partial derivative of this u, this power, minus 2r. Now partial derivative of minus 2r, minus 2 is constant and the derivative of r is 1. So minus 2 is kept constant and we are left with partial derivative of r. And partial derivative of r is 1, so that is minus 2 into 1. Minus 2 into 1 is minus 2, and then writing minus 2 in the front of this function. So that is the first derivative of t with respect to r. Now second derivative of t with respect to r, that is partial derivative of tr with respect to r. So partial derivative with respect to r of tr, this is tr from here, so that is tr. Now that is the partial derivative with respect to r, so minus 2 cos theta will be kept constant, minus 2 cos theta will be kept constant, and we are left with partial derivative of e power minus 2r. Now that is the same as partial derivative of e power minus 2r, just like that. So that is just like that. And partial derivative of minus 2r is minus 2 into 1, multiplying minus 2 with 1, that is minus 2. Minus 2 into minus 2 is plus 4. So that is the second partial derivative of t with respect to r. Now we need tr theta. So tr is here. We need to find the partial derivative of tr with respect to theta. So that is tr from here, and that is because this is the derivative, partial derivative with respect to theta, so r will be kept constant. Now this term will be kept constant along with minus 2, so writing these two outside this derivative, and we are left with partial derivative of cos theta with respect to theta. And we know that the derivative of cos theta is minus sin theta, so that is minus sin theta. Minus into minus is plus, plus 2 sin theta into e power minus 2r, so that is tr theta. Now we need to find t theta, partial derivative of t with respect to theta. So partial derivative with respect to theta of this t is this one. Now that is the partial derivative with respect to theta, so e power minus 2r will be kept constant, and we are left with partial derivative of cos theta, and the derivative of cos theta is minus sin theta, just like that, and then writing minus outside this function and in the front of this term, so that is minus e power minus 2r into sin theta. So that is the partial derivative of t with respect to theta. Now double derivative with respect to theta, that is derivative of t theta, that is t theta. So replacing t theta, and because this is partial derivative with respect to theta, so again minus e power minus 2r will be kept constant, and we are left with the partial derivative of sin theta with respect to theta. And we know that the derivative of sin theta is cos theta. So that is t double theta. Now just look at this. We need to find t theta r. T theta r means derivative of t theta with respect to r. So that is the derivative of t theta with respect to r. This is t theta, this one, replacing t theta by its own value. And now because this is the derivative with respect to r, so sin theta will be kept constant along with this negative sign, so writing these two outside the derivative, and we are left with partial derivative of e power minus 2r. Now partial derivative of e power minus 2r is just like that. You can copy here partial derivative of e power minus 2r with respect to r is just like that from here. So that is the partial derivative of e power minus 2r. This is 1, and now multiplying minus into minus is plus 2, then e power minus 2r, then sine theta. Now just look at these two, t r theta and t theta r, those are looking like same. So that is all about the second partial derivatives. In this slide we need to find the indicated partial derivative in question number 63 through 70. So these 8 questions we need to find the indicated partial derivatives. We are given a function v in question number 68, somewhere here. We are given a function v, log of natural log of r plus s square plus t square. We need to find the third derivative, partial derivative of this v with respect to t, then with respect to s, then with respect to r, and this order. So first of all we need to find the partial derivative of v with respect to t. So that is the partial derivative of this t, and we know that the derivative of log of u is 1 by u into partial derivative of this u. Now this is the partial derivative with respect to t. So this is t, and r and s will be kept constant. So that's why the derivative of r will be 0, derivative of s square will be 0, and derivative of t square will be 2t. So that is 0, 0 and 2t. Now that is actually 2t, multiplying 2t with 1, so that is 2t divided by r plus s square plus t square. So that is actually the first partial derivative of v with respect to t. Now we need to find the partial derivative of this v with respect to s. So that will be the second partial derivative. So the second partial derivative of v with respect to t then s is just like that, writing del s, and we are left with del v by del t. Now del v del t is obtained here, replacing del v del t by its own value, and this is because the derivative of s with respect to s, so 2t will be kept constant. So writing 2t outside this derivative and shifting this term, these 3 terms towards numerator, so that will become just like that, the power will be negative, and that is extended power rule. So using extended power rule, that is 2t, this power will be dropped down, minus 1, minus 1, minus 1, into further derivative with respect to s of this whole base. Now that is the derivative of this whole with respect to s. So r will be kept constant, t will be kept constant, and the derivative of s square will be 2s. So that's why that is 2t minus 2t minus 2, that is 0, that is 2s, and that is 0. Now multiplying 2s with 2t, so that will be equal to 4st. That is the second partial derivative of v with respect to t, then with respect to x. Yes. Now we need to find the third derivative with respect to r of this function. So this derivative is actually del r of del square v by del s del t. Del square v by del s del t is actually this thing. So replacing this value by that value, and that is because the derivative of this function with respect to r, so minus 4st will be kept constant. So that's why we have written minus 4st outside this derivative, and that is we are left with the partial derivative of this function. Now that is extended power rule. Minus 2 will be dropped down, that power will be minus 2 minus 1 is minus 3, into further derivative of this base r plus s square plus t square, with respect to r. So with respect to r, that is 1, that is 0, that is 0. So that's why this is 1, this is 0, and that is 0. Now that is minus 2 into minus 4, minus minus plus, 4 2s are 8, st minus 3, 1 plus 0 plus 0, multiplying 1 with st, so we are left with 8 st, and shifting this term towards denominator, the power will be positive. So that is the third derivative of v with respect to t, then with respect to s, then with respect to r. Now in question number 75, we need to verify that this function is a solution of heat conducting equation. What is heat conducting equation? This is actually heat conducting equation. We need to verify that this function will satisfy this equation. Now for this equation, we need to find the partial derivative of u with respect to t, then partial derivative of u with respect to x 2 times, and then we'll multiply alpha square with this function, and we'll check whether this answer equals to ut or not. So first of all, we need to find ut and uxx. Now what is ut? Ut is actually partial derivative of u with respect to t. So partial derivative of u, this is u with respect to t. We see that this is the product of two functions. This is exponential function, and that is trigonometric function. And in trigonometric function, t is missing, so this whole function will be kept constant and will be written outside this derivative, and we are left with the partial derivative of this exponential function. And we know that what is the derivative of e power u? Derivative of e power u is the same e power u into further derivative of this power. So that's why we have done this thing, that derivative of this e power u is the same e power u into further derivative of this power. Now that is the derivative with respect to t. So minus alpha square k square will be kept constant, and the derivative of t is 1. So that is 1. So 1 into this whole term will be that one, and writing minus alpha square k square in the front of this term. So that is ut is equal to minus alpha square k square into this function. So that is ut. That is very simple to obtain. Now we need to find uxx, the second partial derivative of u with respect to x. So for that purpose, first of all, we need to find the first derivative of u with respect to x. So that is the first derivative of u. This is u function. Now just look at that. That is the partial derivative with respect to x. So e power this whole thing misses x. So this whole term will be kept constant. So writing this whole exponential function outside this derivative, so that is outside, and we are left with the partial derivative of sine kx. And we know that what is the partial derivative of sine u is cos u into further derivative of u, this angle kx. Now that is the partial derivative with respect to x, so k will be kept constant, and the derivative of x is 1. So that's why we have written k into 1. Now k will be written in the front of this term, so that is the first partial derivative of u with respect to x. Now we need to find the second partial derivative of u with respect to x, that is the partial derivative of ux with respect to x, and ux is obtained here. So replacing ux, and that is the partial derivative with respect to x. So these two factors will be kept constant, will be written outside this derivative, and we are left with partial derivative of cos kx with respect to x. So that is now again we know that the partial derivative of cos kx cos u is minus sine of u into further derivative of this u with respect to x. Now further derivative of this with respect to x is k into 1, so that is k into 1. K into 1 is k, and multiplying this k with that k, so that is k square. So this is actually the second partial derivative of u with respect to x. We need to multiply alpha square with this second derivative. So multiplying alpha square with both sides of this equation, so alpha square into uxx is equal to alpha square will be multiplied here, so that is minus alpha square k square into this whole function. That is equation 2. So that is the answer of this right side, equation 2, and that is the answer of this left side, equation 1. We see that equation 1 and equation 2 are same. The value of ut and the value of alpha square uxx are same. So from equation 1 and 2 we conclude that ut is equal to alpha square into uxx. So that is that's why we have obtained here that this given function is the solution of this heat conducting equation. This function satisfies the heat conducting equation, so this function is the solution of this equation. Question number 76 is just like the same, that we need to determine whether the given function is the solution of Laplace equation. This is Laplace equation, uxx plus uyy is equal to 0. A function u is given to us, that is part A of question number 76. A function will be given to us. We need to find the second partial derivative of this function with respect to x, and then the second partial derivative of this function with respect to y, and then we will add both the derivatives. If the answer is 0, then we will say that the given function is the solution of Laplace equation. If the sum of these two is not 0, then we will say that this given function is not the solution of Laplace equation. So we need uxx and uyy. For uxx, first of all we need to find the first derivative with respect to x of this function. So u is actually ux square plus y square, so that is the partial derivative with respect to x. So partial derivative of x square is 2x and of y square is 0, so that is 2x. So ux is 2x. uxx is actually the partial derivative of ux with respect to x. So partial derivative, this is ux, 2x, and the partial derivative of 2x with respect to x is 2 into 1, 2 into 1 is 2, so that is uxx. Now we need uyy. So for this purpose, first of all we need to find uy, which is actually the first partial derivative of u with respect to y. So partial derivative of this u, this is u with respect to y, so that is partial derivative with respect to y. So the derivative of x square will be 0 and the derivative of y square will be 2y, so that is 2y. Now second partial derivative with respect to y is the partial derivative of uy with respect to y, so that is uy, 2y. uy is 2y, so replacing uy by 2y, and the partial derivative of 2y with respect to y is 2 into 1, and that is 2. Now we need to add up these two derivatives. Just look at that, adding uxx and uyy. If the answer is 0, then Laplace, this function will be the solution of Laplace equation, otherwise not. Now adding these two, uxx plus uyy is equal to 2 plus 2. 2 plus 2 is 4. which is not 0. So it means that the given function, this given function, is not the solution of Laplace equation, because the answer is not 0. So that's how we determine that a given function is the solution of Laplace equation. That is the same question, and we have taken the f part of that question. U is equal to e power minus x cos y minus e power minus y cos x. We need uxx and uyy. For that purpose, first of all, we need to find ux, the partial derivative of u with respect to x, replacing u by its own value. Partial derivative of this function with respect to x, cos of y will be kept constant, partial derivative e power minus x, and e power minus y will be kept constant, and that is the partial derivative of cos x. That is the derivative of e power u, and that is the derivative of cos of x. So derivative of e power u is the same e power u, and to further derivative of u minus x is minus 1, and derivative of cos of x is minus sin x. So minus sin x, minus into minus is plus, and that is sin x. I have written this derivative directly here. Now minus 1 into this function is that, and that is just like that. So that is the first derivative of u with respect to x. We need the second derivative with respect to x. So the second derivative of u with respect to x is del x of ux. So that is del x of ux. This is ux, writing this ux over here, and with respect to x, minus cos y is constant and e power minus y is constant. So that's why we have written minus cos y outside this derivative and e power minus y outside this derivative. That is the same as that function. Partial derivative with respect to x of e power minus x, and that is the partial derivative of sine with respect to x. So that is the same e power minus x into further derivative of minus x, and e power minus y, derivative of sine x is cos x. Further derivative of minus x is minus 1, and minus into minus is plus. So that is cos y e power minus x, e power minus y into cos x is uxx. Now we need uyy. So for that purpose, first of all, we need to find uy, partial derivative of u with respect to y. So u is actually that function. Now that is a partial derivative with respect to y, so e power minus x will be kept constant and cos of x will be kept constant, and we are left with partial derivative of cos y and partial derivative of e power minus y. Partial derivative of cos y is minus sin y, and partial derivative of e power minus y is just like that, e power minus y into further derivative of minus y, and further derivative of minus y is minus 1, and writing this negative sign outside, that is minus sign, and this is minus 1. Minus into minus is plus, so that is the first partial derivative of u with respect to y. Now we need the second partial derivative of u with respect to y, so that is the partial derivative of uy, and uy is this one, minus e power minus x sin y, and that function. Now that is the derivative with respect to y, so minus e power minus x will be kept constant, and we are left with derivative of sin y with respect to y, and cos of x will be kept constant. We are left with partial derivative of e power minus y with respect to y. So that is actually the same partial derivative. You can copy and paste here, copying and pasting to get this function, and derivative of sin y is cos y. So uyy is actually minus e power minus x cos y minus cos x e power minus y. Now we need to add up these two second order derivatives, uxx, this thing, and uyy. So now uxx plus uyy, this is uxx from here, plus this is uyy. Now we see that that is plus cos y e power minus, and that is minus, so cancelling these two, that is positive, that is negative, so cancelling these two to get 0. So this equation is satisfied. So it means that this function is the solution of this equation, which is actually Laplace equation. So that's how we show that a given function is a solution of Laplace equation or not.